So hello everyone and welcome to this next lecture. So in the previous lecture, we had simulator run the basic simulation of this buck converter. And we had seen some basic results, which were basically the output voltage plot. And we found that the output voltage is around 7.2 volts. And this is indeed the output voltage we would expect for a modulation signal of around 0.3. And we had also seen some switching signals, and we found that the switching signal can be exactly analyzed according to the modulation signal that we had set and the carrier waveform, which is a repeated sawtooth waveform. So now in this lecture, let's go ahead and look at some other additional parts of the circuit simulator. So before I start with the simulation, I'll just give you a basic brief background and say that if you are interested in learning a complete course on simulating power electronic circuits, I have a complete online course on the platform Udemy, which actually covers the entire process of how you can simulate a power electronic circuit using Python Power Electronics. So it goes through the entire process of installing the software, how to write control code, everything. So if you want a more comprehensive course than what I am currently doing in these videos, feel free to actually check out this course. The link to this course is also provided in the description of this video. So let me go back to the lecture. So now that we have done this, the first thing we're going to do is let me go to the circuit and let us plot these values, and let's plot these currents or voltages. So we already looked at the output voltage. Let me plot the remaining current. So let me plot the input current, the diode current, the inductor current, and the capacitor current. And let's try to make some sense out of it. So I'll just create another plot, and we can just create a plot for each one of them. That's not a problem. So I'll just say input current. The input current is the same as the switch current, so all I have to do is say ammeter IN, I can call it IN, that's alright. Save the waveform, click on done, add another plot. This will be the diode current. And here I just have to choose ammeter D1, and I can call this ID1. Click on done, add another plot. This will be the inductor current. Click on ammeter L1 and say IL1. Click on done. So we have another plot. So we have all these plots showing up. I just want to create all the plots first. And then we can have the capacitor current. And that's exactly what we want, ammeter C out. So we'll just say ammeter C, IC. Click on done. And the last is, of course, the load current. We'll just say load current. Start the plot, and this will be ammeter load. You can just call this iLoad. And click on done. So these are all our plots. So now let's quickly plot them one after the other in quick succession. We might have to zoom in, but the best thing is to exactly have some idea of what we're going to zoom in. First, let's just plot the entire thing. So we should see another one. For some reason, it's showing as a text file. There must be some mistake. Let me just delete it. Sometimes this does happen. All we have to do is click on it again. I don't know whether it's an operating system mistake or it's a bug somewhere else. A .png file shows up as a .txt file. I don't know if it's something just to do with Linux, or maybe it also happens in Windows. So let me just plot on it again. And yes, now we do see it is a .png file when the operating system has seen it as a .png file. So this is the current. As of course, we can't make any sense out of it. So let me plot a smaller range. Let's call this let's say 0.58 to 0.6 or 0.59 to 0.6. I mean, this is just a random choice I've made. You are of course free to choose anything else you want. Then go over. Yeah, we do have something, but I think it's still a little too much. So let's do half of this, or let's say even we just need 0.59 to 0.592. So let's go over and click on 0.5, 0.59 and 0.592 and click on plot. So let's go over. I hope this is a better plot. Yeah, this is a decent plot. So what we do see, this is the input current, and I don't know why it's appearing thrice. Was there a mistake somewhere? Well, no, there's only one. I'm surprised. Anyway, so let me quickly plot the others in the same range. And this is the diode current, and this appears okay. So there might have been some other problem. Maybe I made a mistake in actually choosing it. So this is the diode current. Let me go back to my circuit simulator. Let me plot the inductor current. And this is the inductor current, perfectly fine. And this is the capacitor current. Also interesting. The most important thing will be when we actually put the plots together and actually try to analyze them. And we just click on 0.5, 0.592. So this is the last plot, that is the load current. And this is the load current, nice and steady voltage. And the reason is pretty simple, because we have a steady output voltage, almost steady. And the result is the output voltage is applied across the resistor, so the resistor just draws an almost constant current. Of course, there is some fluctuation because the output voltage does have some fluctuation. So now that we have all this, let's start analyzing them. So this is the load current, which is pretty straightforward. Let's close this for now. And let's look at the others. So now, the most important one is, or rather, the most important ones. Okay, I understand. Okay, so let's look at the inductor current. This is a very good plot. And at the same time, let's pick out the diode current. So let's place these two next to each other. Now, I didn't want to expand on this. So yeah. So the main thing about this is, the way it works is, the inductor current is the current through this inductor. Right? This is the current through this inductor. And the current through this inductor is flowing in two stages, right? There are two states in which it flows. There's one part where it flows through the switch and the other part where it flows through the diode, right? So it will be interesting to compare the diode current, the switch current with the inductor current. So let's do that. Let's put the input current, the inductor current. So I have the input current, the inductor current, and let me put the, just a minute, I'm having some trouble with this operating system. Yeah, and finally the diode current. So let's have these three. So this is actually the inductor current. If you actually look, the switch current is flowing in one particular cycle, and the switch current will flow. When the switch current flows, the inductor current is actually rising. Right? Now, the way to actually do this and to compare these two is to plot these two waveforms together. Right? So let's do that. Let's go back here and create another plot and call this inductor and switch current. Start the plot, choose inductor, call it IL1, save the waveform, choose another one, call this input, and call this I inp, and save the waveform. We have two waveforms, we are done. So let's go all the way down and plot these two. So we have 0.59 and 0.592. So this is the inductor and switch current, and here you can see exactly what I was talking about before. When the switch is on, when the switch is conducting, you see this is the orange line. So the orange line is the input current or the switch current, the blue line is the inductor current. When the orange line is not zero, you see the orange line jumps up immediately to this point. When the orange line jumps up to this point and it starts rising, that's when the inductor current is rising. This is when the switch is turned on. So when the switch is turned on, the inductor current rises. That same current is now flowing through the switch, which is why the two currents are the same. When the switch turns off, the switch current goes to zero, but the inductor current continues to flow. And to understand that, we just have to come down to the other one. That is, we need to come down to the diode current plot. So let's plot this and this. And you see, now you can compare these two currents. When the switch is turned off, the inductor current decreases, but the inductor current is decreasing through the diode. So the inductor is freewheeling through the diode. Right? So this is when the inductor current continues to flow, but through the diode instead of the switch. So the transfer of the current happens from the switch to the diode. Right? And of course, you are welcome to create another plot to compare these two. Now, the other aspect of this is what happens to the switch current, the capacitor current. So now the capacitor current, to understand the capacitor current, all we have to do is we can plot the inductor current and the capacitor current. So yeah, this can remain the same. I'll just call this IC. And I just have to add the inductor current and call this IL. And to this, let me also add the load current and call this load. Save the waveform and click on done. So let's come all the way down here and plot this for the same range. And you see the difference. So basically, in this plot, you can clearly see that the inductor current, the ripple, passes through the capacitor current, through the capacitor. You see, the ripple of the capacitor is exactly the same as the inductor current. The DC component, or the average value of this inductor current, is what continues to flow through the load. And this is the filtering action that takes place through the capacitor. Right? The capacitor behaves as a filter, pulling out all the harmonics in this inductor current, and what remains is that DC current that continues to flow through the load. And the result is, even though the capacitor pulls in such a current, it still produces a fairly smooth voltage, because that is the nature of the capacitor. The capacitor acts as a filter, right? Because the voltage is an integral of the current, so therefore even if the current contains high frequency components like this, the voltage is still reasonably smooth. Right? So this is the working of an inductor. Now, there is one more case in which you can actually look at the inductor, and that is you can actually change the load of the inductor. So, for example, in the circuit parameters, we had taken one particular case, that is, we had taken a few values. One thing that you could consider doing is, you could change the value of the inductor or the value of the resistor load. So, for example, if you decrease the load, and let's say I make this 1000 ohms, which is a very low resistance, now the buck converter goes into what is called as a discontinuous conduction mode, because when the load is very low, the current through the inductor will fall to zero before even before the switch can start conducting again. So we can actually check out that result. So I can just run the simulation. Let's just go to the command line, make sure that there is no error, there is none. And let's close these plots because we need a new set of plots. And here, the simplest current plot, of course, is the inductor current. So let's just plot this inductor current. This is the inductor current, and we can just plot maybe the last point, that's 0.004205. No, I plotted the wrong one. I was plotting the inductor current. And here you can see the result. The result is the inductor current is now falling to zero. So the inductor current rises when the switch is turned on. It falls through the diode when the switch is turned off, so the freewheeling does happen, but the current reaches zero before the switch turns on again. This is called discontinuous conduction mode. If you compare it to the previous conduction mode where the current was always flowing through the inductor, now the current flows to zero, which means there is a state, there is now a third state. The switch and the diode are both turned off, right? This is called discontinuous conduction mode. The previous was called continuous conduction mode because the current was always flowing. The current was never zero. It was always above zero, right? So these are two different cases of the buck converter, right? So I'm going to stop this lecture right now because I don't want it to get too long. If you have any doubts, please do post in the comments. Otherwise, I will see you in the next lecture where we'll just do a bit of cleanup of this final simulation and so that we can get started with the next circuit in a few lectures from now. So thank you so much and see you soon. Goodbye for now.